I did want to start off today by just going over the answers to the warm-up you're just working on. I'm going to ask a couple of questions after we go over these answers. So for starters, number 1, square root of 4, that's just 2. Did anybody have that as plus or minus 2 in the room? No? Well, rightfully so. You know, you wouldn't record that as plus or minus 2. Here's the question I have for you. Does anybody know why they didn't include the plus or minus 2? Why you dropped it? It's good intuition if you did. Why do we not include the plus or minus for this? Do you know? Why don't you throw the square root of 4 in your calculator, hit enter. What does it give you? 2, not plus or minus 2, right? Just plain old 2. Okay, so that is definitely a true story, Chris. You're right about that. You cannot take the square root of a negative number. I could definitely see that coming out on your tests when I was looking at them. You guys stopped. You're like, no real solution, can't go any further. So that part of your test actually looked really, really good. That is true, but not the reason why we don't include plus or minus here. We did include plus or minus when we were solving for x. Do you remember? Like if it said x squared equals 4, you took the square root of both sides, you included your plus or minus. You guys were pretty good at that. There was a problem on the test where you had to do x squared equals 14, or I'm sorry, x squared equaled 196. You took the square root of both sides, you got plus or minus 14. So that looked really good. You guys did a nice job with that. But that's not the same as this. We're not solving for x, Jonathan. No, negative 2. Quantity squared, negative 2 times negative 2 is positive 4. The idea here, little, sort of paradigm shift for you folks. The square root of 4 in this particular problem, we actually read this symbol right here. In case you haven't heard this in a while, this is read as the principal square root of 4. When you type it into your calculator, that's what your calculator is interpreting your input as. The principal square root is just another phrase for positive square root. So for these particular problems that we're going to take care of initially in this chapter, long story short, moral of the story if you will, you don't have to worry about plus or minus on your problems today or on your worksheet for tonight. We don't actually need to think about it again until we go to solve for x. That's when you have to give me all of the different possible options for an answer. And that's when we had to include our plus or minus. So for the problems today and tonight and for a while, we don't have to worry about the plus or minus. So in number 2, when you do the square root of 100, you should have just gotten 10, not plus or minus 10, which it sounds like you guys did. Number 3, do you see how the answer there is 10 root 2 or 10 square roots of 2? Who got that right? Just curious. Good job. Okay, so today is going to be a pretty easy lesson for you folks that got that right. So it's about half of you. Good job. Can anybody talk to me about how you do those? Go, John. Yeah. Yeah. But you did a nice job. You have to find the largest perfect square factor that goes into the radicand. And after that, you use your product property to break the radical apart. Did anybody pick 25 to go into 200 when they broke it down? But then you had to do it again? Oh, okay. So 4 was your perfect square factor, but then you had to simplify the square root of 50 again. Yeah. So you can pick, inadvertently not the largest perfect square factor, but then you always have to remember to reduce and reduce and reduce. Yeah. So it can be a little bit tedious. Question number 4, how I got the answers, well, for me is from memory, but you folks want to remember that if it asks you for a perfect cube, what you're doing is, for instance, 1 cubed. That's 1 times 1 times 1, and that's 1. 2 cubed is 2 times 2 times 2, that's 8. 3 cubed is also a perfect cube. That's 27. 3 times 3 times 3 is 27. 4 cubed is 4 times 4 times 4, it's 64. 5 cubed is 5 times 5 times 5, which is 125. You should bank on memorizing these 5 numbers. they're just like your first 20 perfect squares that you had to memorize from back in the day. So these numbers here you should be able to produce pretty quickly from memory as well. Now you folks went through the vocabulary already. Anybody have any questions about those words? Essentially, we have three properties that we're going to address today, and you jotted them down from your textbook. They do have some names. In our old textbooks, you folks are dealing with new textbooks right now, but in our old textbooks, this third property, do you see how it indicated division? We called that the quotient property. This second property right here, because it dealt with us multiplying radicals that had the same indices, we call that the product property because it was multiplication. And then this guy up here never had a name, but it's super cool. Your next quiz, looking like next week sometime, is no calculator. So what you have to think about is how could you make the problem a little bit more manageable using the numbers on the paper? And that's what this first property does for you. If you don't have a calculator, it's kind of hard to take, initially maybe the cube root of 64, if you don't have that number memorized. But, what you can do is just take the cube root of 8, which is 2, and then square it. 2 squared is 4. So that property gives you the flexibility to kind of move that exponent in and out of the parentheses. Do you see that? So it's a nice property to have. It's going to make life without a calculator a lot easier. So there it is underneath the radical, or you could bounce it outside and do the radical first and then use the exponent. I really like that property. Okay, so let's practice. We're going to practice using your properties, just those first three. So here in example 1, we're asked to use those three properties of radicals to simplify each expression. So for part A, do you see how we're multiplying the two radicals together? That's my visual cue to use the product property. What I can do, or what the product property allows me to do, is when these indices are the same, indices, that's the plural for the word index. Some of you might notice the root. When those numbers there are the same, we're actually allowed to multiply these together and put them underneath one radical. So the cube root of 4 times the cube root of 2 is actually the same as the cube root of 4 times 2, which is the cube root of 8. Now what's nice is that I remember that number from my warm-up. I remember that the cube root of 8 was a very important number. You folks had to list out your first 5 perfect cubes, and I'm hoping that you'll see them enough that they become part of your memory. But 8 was that second number you wrote down, which means you can take the cube root of that number and it works out nice. The cube root of 8 is 2. Part B is that classic case where, like, oh my gosh, if you don't have a calculator, no, what are your options? Well, if you see there, I have the square root of 5, and then all of that is squared. Some of you might recall from the last chapter that a square and a square root actually undo each other. The answer would be 5. However, if we use this first property that we talked about today, I know that I can rewrite this. I can actually rewrite this as the square root of 5 squared, which is the square root of 25, which is another reason why this particular expression evaluates to 5. That's kind of neat. Different way of looking at it. Part C is another case where we can use the product property. I have the cube root of 5 times the cube root of 25. And whenever I see that those roots are the same and I'm multiplying them together, I can exercise the product property. So this is actually the same thing as taking the cube root of 5 times 25, which is the cube root of 125. And then I recall from my warm-up that 125 was actually a perfect cube. Cube root of 125 is just 5. And then lastly, we have the square root of 50 divided by the square root of 2. See that division right there? That lets me know I can exercise the quotient property. Another thing you should bear in mind is that there is a little 2 hiding out in there. I don't know if you ever knew that that was there or not. We write the square root so often that they just drop the 2. But when there is no index, you can assume that there is a 2 hiding out in there. It's like we're taking the square root. So With this being said, I do have my indices the same, which means that I can exercise the quotient property. Now, much like the product property, I could glue my product together underneath one radical. I could put my quotient together underneath one radical too. So this is the same thing as the square root of 50 divided by 2, which is a lot more manageable without a calculator. So the square root of 25, square root of 25 is just 5. Questions about that? Okay, we're going to apply the product and quotient properties in a slightly different way in the next example. This time, we're not going to glue things together underneath a radical. We can also use our product and quotient properties to break radicals apart. So, oops, I forgot about this part. Before we go into the next example, there's some rules we follow, however. These are some rules that are outlined on page 20 in your book, but they're the 3 rules we have to follow for a problem to be completely done. So these 3 rules kind of help you answer the question, Mrs. Lucas, when do I stop? Number 1 sort of addresses the issue from earlier, like, how do we know a radical is completely simplified? Number 1 says, hey, a radical is completely simplified if you've taken out all of your perfect roots that were factors of your original radicand. So you've gotten rid of all those possible factors underneath the radical that could be eliminated. Number 2, this will pertain a little later on in the week, so this one's not so big of a deal right now. All of your fractions have to have denominators that are radical free. We never leave a radical in the bottom of a fraction. That's called rationalizing the denominator. We'll take care of that in a couple days. So that one you don't have to worry about, as well as rule number 3 there, you don't have to worry about that one yet either. We're going to take care of that in a couple days as well. She is. Thank you. Whoops. JK. Last period. She left. No, you're fine. I'm sorry. I thought she was here. Everybody have their rules copied down? You're good? Alrighty. So, now, in example 2, this will be my last example of the day. Example 3 is ultimately going to be a little bit of independent practice for you. In part A, we have the square root of 32. And here's the question you need to keep asking yourself when you go through these problems. We're going to write the question down in a little thinking cloud. So you're going to draw yourself a little thinking cloud right now, like this. Here's you thinking about how do you simplify the square root of 32. You know, rule number 1, since we're starting a new note packet, what goes on the smartboard goes in your notes. And then if you don't understand it, don't write it down. Just ask me a question, and then we can answer your question and carry on with our notes. The question we have to ask ourselves is this, and John said it earlier. This was your question. What is the largest perfect square factor that divides into blank? What is the largest perfect square factor that divides into blank? And in this case, we're thinking about the number 32. So we have to ask ourselves in our list of perfect squares that we have memorized. They're also on my door right there, on my closet door. We have to ask ourselves, what of those numbers is the largest that divides evenly into 32? What do you think, John? Yeah, good man. So I'm going to use the product property, but this time I'm going to use it in reverse. I know that 32 is equal to 16 times 2. So what I'm allowed to do, based on the product property of radicals, is say that the square root of 32 is now equal to the square root of 16 times the square root of 2. And then you just square root each piece. The square root of 16, that evaluates to 4. The square root of 2 is actually what we call an irrational number. It's a non-terminating, non-repeating decimal. Crazy decimal. So if you want to tell me that that's a part of your answer, you just write it there. This is what we call the exact answer. No rounding involved. Now, you have a worksheet for tonight. I'm not done. I'm going to show you the rest of these. You have a worksheet for tonight. I just wanted to show you real quick how you could use your calculator to verify that this is a true statement. I'm telling you right now that the square root of 32 is the same as 4 root 2. So check this out. You go into your calculator, and what I'm trying to tell you right now is that the square root, second x squared, 32 is the same as 4 square roots of 2. Do you see how you get the exact same decimal? They have the exact same value. They're equivalent expressions. This is how you're going to check your work tonight. You're actually going to put it in your calculator to check to make sure that the problem works out to equal what you have it simplified down to, because you don't have an answer key and you don't have a back of the book for this worksheet. So you're going to use your calculator to help you check. So that's the last step. I have a question for you. Why can't I just put the decimal down, like 5.66? It's not exact. Very good. What's that mean? Right, right. You could end up rounding differently than maybe a textbook would want you to round. That could be true. Anytime you round, true story, I think I've talked about this before. You introduce a margin of error into your answer. Like you make an approximation, which automatically isn't exact, just by nature of the definition of what an approximation is. So if you were going to tell me, hey, Mrs. Lucas, it's 5.66. Well, you rounded correctly. You did a nice job with that. That's not my contention. What I'm contending is that your answer is 1/100th off. It's just a little bit wrong. And you would have to round these no matter what. It's not like you're going to get like, ooh, 7 for these problems, because there's irrational numbers in them. So just to show you that part again. Do you see how the square root of 2 is part of our answer? That's a crazy whacked out decimal. Anytime you take a rational number times an irrational number, the product is always irrational. That's true. Take anything times pi. Irrational. All right. Mrs. Lucas, completely irrational. I'm just kidding. Sort of. All right. 75. We have to ask ourselves, what is the largest perfect square factor that goes into 75? Go, John. Yeah, 25 times 3. Square root each piece. Square root of 25 is 5. Square root of 3 comes along for the ride. So what I'm postulating with you right now is that the square root of 75 is the same. It's 5 root 3. It better be, or I did it wrong. Bam. Do you see how they're the same decimal? Works out. I've produced the exact same decimal approximation for both. So I know I did that problem correctly. Part C, square root of 125. What is the largest perfect square that goes into 125? Bless you. Good, Eddie. Yep. 25 times 5 gives you 125. Square root each piece. Square root of 25 is 5. Square root of 5 is an irrational number. So there's your answer there. What's up? You may. Oh, wait. Can you wait 1 second? I just want to show you how to do cube roots, and then you can go. Hey, Tammy, can you do square root of 18? Good. And then what'd you get when you simplified it? Nice job. Okay, cube roots just real quick. We use the product property on these, too, to break them apart. So when I look at the cube root of 81, the cube root of 81, the question I have to ask myself this time around changes just a little bit. In the first part of the problem, I had to ask myself, well, what is the largest perfect square factor that went in? Now I have to decide what is the largest perfect cube factor that goes into 81. So for this, you probably want to look back at your warm-up. You have to ask yourself, which of these 5 numbers right here, 1, 8, 27, 64, 125, which of those 5 numbers now divides evenly into 81? Does anybody know it? John? Yeah, I heard it in a couple places. It is 27. Good job. Turns out that 81 is 27 times 3, I think. Yeah. Yes. And then I have to cube root each piece. Hey, people, this is important. People that are good at math pay attention to the details. Did you see that there's a little 3 there? Please be mindful of the fact that that 3 is not there for decoration. It's not the holidays just yet, right? I'm not like decorating a Christmas tree. That 3 indicates that you had to do the problem in a slightly different way. Do you see that? So it's a different question altogether than the ones above it. I had to actually do the cube root for this problem, not the square root. That's my visual cue that I'm looking for perfect cubes. So I take the cube root of 27, I get 3 cube roots of 3. Now, how do you check that on your calculator? Because that's been a while, right? I'm going to show you real quick. Tammy, if you're okay, you can go, but I'm going to show you how to check this on your calculator. Cube root of 81. If you're wondering where the cube root button is, it's been a while. It's math and the 4th option down. So math, 4th option down, 81. Press enter. What I'm postulating with you today is that that is equivalent to 3 math, option 4, cube roots of 3. And I get the same decimal. Do you see that? So I produced equivalent expressions. One's just a simplified version of the other. Let's do it one last time, and then I'll cut you loose on your independent practice. Cube root of 16. I have to ask myself, what is the perfect cube factor that divides evenly into 16? Out of those 5 numbers you had in your warm-up, which one goes in, Eddie? 8. So I have to cube root each piece. Cube root 8, that's 2. And I bring down the cube root of 2 for the ride there. So technically speaking, the cube root of 16 should be the same as 2 cube roots of 2. So I'll put that in my calculator. Oops. Sorry. Typo. Math 4, 16. So this number is indeed the same as 2 times the cube root. Nope. Two cube roots of 2. And you do get the same number, so it does work out. You good with that? Okay, so now for your independent practice, just to wrap up today's lesson, I wanted you to get going on example 3 there. So that's a little bit of practice for you. Just a little reminder, when you see numbers outside the radical, like in part C, you know that you just multiply those together as you normally would. You could just use your associative property of multiplication to regroup that a little bit. So if you're looking at part C like, oh my goodness, how do you do that? You take the integers and multiply them together, and then you take the radicals and multiply them together. So that's your little tip to get you started on that one. But yeah, you want to go ahead and start on that, and I'll show you some answers here in a sec.